monitoring that for, I will be monitoring that for Larry. Larry's also planning on giving breaking in his presentation to give time for questions. But if there's something that's pressing and you want to put it into the chat, I can make sure that I read that and address it with Larry if necessary. So with that, we are very excited. I can tell you that Larry has been one of the most influential people that I've had to work with, and has really influenced me and my career. And so you guys are in for a treat tonight. So Larry, with that, please go ahead and get started.
Okay, thank you for that glowing recommendation, introduction. I first of all want to make sure that you recognize that this is not going to be death by PowerPoint. All right, so I'm planning on, I think there's a total of 27 slides in my presentation, and I'm going to stop every 8 or 9 or so and allow for an opportunity to ask questions. And if anything there are burning, we'll break out and talk about it. But we're not going to have breakout rooms because there's too many people to do that. But you won't have to wait till the very end. You also should know that I prepared a narrated version of the PowerPoint that I'm using, so you can listen to it at your leisure without necessarily having to watch the recording of this, although I'm sure that would work as well. So without any further ado, I am going to see if I can find my and switch into play. Okie doke. So it's interesting, in the chemistry workshop that I did many years ago, one of my participants said, we usually put chemistry or energy, the treatment of energy, near the end of the year, and we hope we don't get to it because I'm not comfortable talking about it. And I think that might reflect how some of you feel, and I'm hoping that we'll make this a little bit easier. Modeling instruction does a great job. Okay, we use the idea of energy as a currency of change, faster or slower, higher or lower, hotter or colder. Either you pay somebody or somebody pays you. We use this substance metaphor. Now we know that energy is not substantial, but we use a substance metaphor to describe it. And energy as money is one of them. Energy as information is another. We can talk about that if you like. It's stored in various accounts, like savings or checking. And there are transfers between the system and the surrounding. They're like deposits or payments. The storage mode or transfer mechanism does not affect its nature. So we're not going to talk about transforming energy. Okay, why am I not advancing? All right, there are 4 big ideas. 1, energy can be viewed as a substance-like quantity that can be stored in a physical system. It has to belong somewhere. When energy moves between accounts within a system or transferred between system and surrounding, we observe change. In fact, we infer the role of energy by observing changes in matter. Energy maintains its identity. So I have been really working hard to expunge transforming energy from my vocabulary. And finally, energy is conserved. Now, everybody has the standard definition, oh, energy can't be created or destroyed, blah, 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 blah. We just say the total amount of energy in an isolated system is constant. And I am still, maybe because I'm a host here, and well, you saw that one, that was pretty fast. I want to go back. So there are 3 transfer mechanisms, and they are between system and surroundings. One is working. That's the process by which energy is transferred in or out by an externally applied force. If I were doing this in person, I would be pushing on somebody in a roller chair, wheeled chair across the way, and showing that I could increase that person's kinetic energy by applying a force. And so Erica, you might be able to help me figure out why I am not able to advance my PowerPoint.
Do you see the little arrow down in the bottom? Try that. Nope, that's back. Yeah, I mean, yeah, if you want to go back.
There we go. I
Yeah.
could do it that way.
There you go.
Heating is the process by transferring through the collision of myriad of microscopic particles. This occurs when there's a difference in temperature between system and surroundings. And radiating, the process by which energy is transferred by the absorption or emission of photons. Okay. We use gerunds rather than nouns. We don't talk about work, heat, and radiation because we want to emphasize that these are processes, not forms of energy. I've seen too many books where they have chapters called heat and energy or work and energy. That's really like saying work or energy and energy. It's okay to use work or heat as shortcuts rather than saying the amount of heat transferred by working or heating, but we want to make sure that people don't think of them as separate things. So I say heat is a great verb, but it's not such a great noun. So you can see that. Can I turn this guy off? Yes, I can. Good. So the storage modes. Energies, there's two ways that we can store energy. It's either in the motion of parts of the system, translational, rotational, kinetic energy, E sub K, or thermal energy. Or energy can be stored in fields. Now, it took me a long time to become comfortable using the F word, but NGSS emphasizes its use. That's due to the arrangement or configuration of parts of the system. It's often referred to as potential energy. We're going to talk about why that's not so useful. And it can be stored in a gravitational field, magnetic field, and the electric field, which includes elastic, phase energy, and chemical energy. Okay, so since fields are not easily imagined, we need some representational tools that help to do the job. And what I'm going to do is to switch over to a little video, and it looks like I'm I'm going to do this one. So this is about a little 5-minute video clip from the mechanical universe and beyond. And I hope that you can hear the sound. If not, I'll stop it and restart it.
Electricity, as well as magnetism, applied real forces in space, and he began his study of them with a number of assumptions. Anywhere in the vicinity experiences a force. If it's due to only one charge, the pattern of forces detected by the test charge is simple. The pattern's more complex for two opposite charges. Or for two charges of the same sign. and more complex still for more complicated arrangements. But in any case, here's the point. Even if the test charge isn't there to feel it, the pattern of forces can be imagined to exist everywhere in space. This is the essence of the idea of the field. And although Faraday only imagined it, the field can also be expressed mathematically.
The force that acts on a test charge at each point in space is equal to the test charge times a quantity due only to the other charges. That quantity is the electric field.
Don't you wish you could do algebra that way? Okay, just in case you hadn't picked up on it, the red spheres are positively charged and the light pale blue spheres are negatively charged.
Faraday never arrived at that definition of the electric field. But by seeing both electric and magnetic phenomena as forces in space, he managed to see further than his peers. As a result of this, and many other discoveries, he eventually became director of the research laboratory at the Royal Institution. And succeeding Davy, he became the professor there, as well as a member of the Royal Society. But it was as researcher, rather than instructor, that he saw deeper and deeper into the invisible forces of space. To Faraday, the 1/r² force between electric charges suggested that the force must be applied by something radiating outward from charges. Something which, like light from the sun, never stops and never ends in space. As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path. These lines of force would begin only on positive charges and end only on negative ones. And they would flow smoothly through space, never crossing or tangling. No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together, and weak far from the charges where the lines are farther apart. The ability to apply a force resides at each point in space, and the force arises from the intensity of lines, regardless of the location of the charges that create them.
Okay, so let's revisit this. And then I'm going to pause to answer some questions. I want to talk, I made a distinction earlier about kinetic versus thermal energy. Why do we have a distinction in modeling instruction? Well, kinetic energy is great for describing the energy stored in the motion of small point particles that are not interacting with anything else. Baseballs, bricks, monatomic gases. It's the primary motion storage unit mode, in physics. Thermal energy is more appropriate to describe the energy stored in the motion of a large collection of interacting particles, like in a liquid or solid. It's the primary emotional storage energy in chemistry, storage mode in chemistry. What's different about thermal energy? Well, particles in a solid undergo primarily vibrational motion. As the kinetic energy of particles increases, the elastic energy decreases, and vice versa. I'm going to show you a little video clip from Eureka to help you picture that. This is molecules in liquids.
All calm and collected and cool. If we could look at what's going on inside it, we'd see that its molecules are equally calm and collected, vibrating happily away in their latticework to a steady, even rhythm. Each pair of molecules being brought together by a mutual force of attraction, and then pushed apart by a mutual force of repulsion. Fine, until the heat of the sun gets to them. As the sun gets hotter, the molecules become more and more excited and go faster and faster, swinging to and fro more and more wildly. The hotter they get, the faster they go, until the inevitable happens. The force of attraction is no longer strong enough to hold them, and they burst apart as if snapping an invisible spring.
Okay, so back to this, and this is my last slide before the break. So if you were watching Molly and Marvin, the two molecules vibrating back and forth, you may have noticed that when they got to their extremes, they were slowing down, their kinetic energy was low, and as they were moving toward one another, they sped up. So when their elastic energy decreased, the kinetic energy increased. On average, in the condensed phases, the kinetic and elastic energy of the particles are equal. Any addition of energy to the system via heating will be equally split between these two accounts. So it takes twice as much energy to produce the same effect on the kinetic energy in a metal as it would for the kinetic energy in a monatomic gas. That's why we use thermal energy as a better descriptor for motional storage in chemistry. Okay, so I'm going to pause and stop sharing my screen for a second. And give you a chance to I only see one comment in the chat. Does this mean everything is perfectly clear and we can move on, or are you just being polite and shy or something like that? Okay, so one of the things that I do in my workshop is to use fist to 5 to see how well you're making sense of what's going on. If you are totally confused by what's going on, you would hold up a fist. If you think, geez, I could do a better job presenting this than Larry, you'd hold up a 5. So I'm going to ask you to hold up a certain number of digits. If you're a 1, just be careful which digit you show me. So let me know where you stand on what we've been doing so far.
And Larry, there is one question. There's a new question in there.
Well, so Brian asked, how is phase energy part of the electric field? Phase energy is stored in the electric field because there are electrical interactions between the particles. It's not gravity, it's not magnetism, it's electrical interactions. I hope that helps. Okay, fist to 5, where are you guys? Hold your hands up so I can see them. Okay.
So I have a question. Hi, thank you for doing this, number one. I actually just came across this summer. I've switched over to doing, for the first time, complete modeling in chemistry. So I spent the summer trying to understand this. I always envisioned that the energy was a push-pull between IMF and forces of repulsion, and that the heat energy was the result of the collision of those. I'm having a difficult time understanding. I did not do well in physics. I got passed by giving my teacher Dunkin' Donuts and coffee every day. And I'm going back to the 70s. So there you go. It's a long time. So I'm a little confused on the elasticity versus why elasticity is decreasing if kinetic energy is increasing or vice versa.
I don't have a spring in front of me. I should have thought to do that, but imagine a spring holding my two fists together. Okay, so as you pull these apart, the spring would get stretched, the elastic energy would be greater, and then at the extremes, when these things are vibrating back and forth, they are stopped here and they're stopped here, but they're most rapidly moving in between. So energy is shifting back and forth between elastic and kinetic accounts.
That makes sense.
Because of that, any amount of energy that you supply to a solid or a liquid is split between those two accounts. So it takes like the molar heat enthalpy for gases is monatomic gases is half as great as it is for a liquid or solid.
Okay. All right. That makes sense. Yes.
Excellent. Okay, I'm going to move on. If you're
One question.
One question.
Larry, would you say when you are using the term isolated, what do you mean?
Say something in a well-insulated container, perhaps? Something that's not interacting with its surroundings? How would you, in a physics first perspective, explain why the increase in energy transferred to a system results in increased particle movement? Well, I would think that working would be the primary energy transfer mechanism for a physics class, where you are applying forces to the particles. And if you apply a force to a particle, you're going to get it to speed up or slow down. If it's okay, I'm going to move on. Share my screen. Boom. So energy and fields. Play from this slide. So far, so good. So let's talk a little bit about fields. I sort of jumped the gun a bit on this slide. We believe that particles with mass or charge or magnetic moment both produce and respond to a field. Back in the old days, when I didn't know any better, I thought a field was sort of a map that would explain what forces would be acting on a particle if a particle were placed in the field. But actually, the field is the agent that mediates the interaction between particles. If you don't believe in the field as the agent, then you have a problem because you're thinking about action at a distance. These two particles are interacting with another without touching. Well, they don't touch, but the field is between them, and it's the thing that's doing the work. Particles subject to attraction or repulsions will spontaneously move to a lower energy configuration if they're free to move. Changing the configuration of particles changes the energy stored in the field. When you saw that little mechanical universe clip, if you move those little particles around, you would see that. It always requires energy, and this is our lodestone in modeling instruction. It always requires energy to separate bound particles. You can take little neodymium magnets and try to pull them apart, and kids easily see that they have to put energy in order to separate them. And when those magnets come snapping back together, you better make sure your finger's out of the way. As the particles become bound, they give up their energy to the surroundings. The rubber band metaphor can help students visualize this process. Now, why are we opposed to the use of potential energy? Well, first of all, it's an unnecessary, non-helpful adjective. All the students I know have people say, their teachers tell them you're not working up to your potential. All right. So what does it mean? It doesn't help students understand where the energy is stored. It can lead to the naive conception that the energy belongs to a single particle. If an agent here, this hand, lifts this ball into a higher position, the ball doesn't have gravitational energy. It's the Earth ball system that stores the gravitational energy, and it's stored in the gravitational field. So in physics, we use gravitational energy, elastic energy, electric energy as our primary potential energy storage modes. In chemistry, phase energy and chemical energy, manifestations of that electrical field. In biology, chemical energy is sufficient. So while NGSS still uses the term potential, the disciplinary core idea is elaborated by using this language. And I'll let you read that here. Energy associated with the configuration, relative position of the particles. Now, let's talk a little bit about potential energy wells. If you're in physics, you certainly have seen these before. In chemistry, maybe not so much, but I'm going to stop this and show you another little video clip, which might help you picture where these energy wells, what we're talking about. This comes from the ChemThink covalent bond tutorial. I've just clipped out about a 10-second or 12-second portion of this. So we have two particles here, two atoms with, they're hydrogen atoms in this case. They have a proton and an electron. Watch what happens as they come together. So when they get too close, the particle, the energy increases and the particles move apart. There is some optimal position that would be the equilibrium bond position for two bound particles. That's their lowest energy state when they're at an optimum distance. That's when the attractions are maximized. This is a potential energy well. All right, so back to this thing. You look at the potential energy well for reactants and products, and you can see that the products store less energy due to the attractions. Remember, attractions reduce the energy of the system. Repulsions increase the energy of the system. Well, if you're a chemistry teacher, you might say, I'm not sure I've seen that one before. Oh, I got to go back to play from the current slide. Come on, there we go. But any chemistry teacher certainly has seen a diagram on the left-hand side. That's your potential energy curve and reaction kinetics. So in essence, the region where you have reactants and products are basically the bottoms of the energy wells for the reactants and products. And the peak here is the activated complex. Well, all we've done, and ordinarily the definition in physics is we say there is zero potential energy when the particles are infinitely far apart. They're not interacting. As they come closer and closer together, the energy of the system decreases. Well, if we move the zero position down lower, and I tell you, you look in any chemistry book, you will not see a scale on the vertical axis, all right, because they just don't define it. So we just make the zero down lower, and then we represent these negative quantities with bars, because it's easier to compare positive quantities than negative quantities. And that's what energy bar charts are all about. It's useful in both physical and the life sciences. The energy accounts may have different names, but the concept is the same. In my school, when I was teaching, we taught these before the physics teachers because chemistry came before physics. When the physics teacher got there, the kid said, oh, We've seen these before. Names are different, but the idea is the same. And these energy bar charts help to reinforce the consideration of what constitutes the system and what are the surroundings. Okay, physics should be taught first because it's the simplest subject, okay? And here I have a system where I have a roller coaster cart against a compressed spring, and the initial position is, let's see, what I must have jumped in here, is I've got a cart, earth, and spring in the system. Working is the primary energy transfer mechanism, but I'm not going to have any external agent acting on the cart because I put the spring in the system. So all of the energy is being stored as elastic energy in the spring. When the spring is sprung and it applies a force to the cart, then the cart moves along and now it's higher off the ground. So the earth cart system is far separated. So there is gravitational energy and the cart is moving along. So there's kinetic energy, and the amount of energy afterwards better equal the amount of energy before. Having this representational tool helps make it easier to write equations to describe what's going on. So I can use this equation. That's the energy, elastic energy in the spring. Come on. This is the kinetic energy, and that's the gravitational energy. And I can solve for any one of these variables. Chemistry is a little bit harder because sometimes the system is not as easy to define. For example, if you spill some water on your shirt, is the water in the system, the liquid water in the system, or is it in the surroundings? As a general rule, we like to say anything that undergoes structural change will put in the system, and the parts that only undergo changes in temperature could be in the surroundings. But that doesn't mean you have to do it that way. There's more than one right way to answer this question. I have, in this particular case, an energy inflow from the surroundings that's increasing the phase energy when I'm going from liquid to gas. And I'm only treating that portion that has evaporated. In reactions, we tend to ignore phase energy because that amount of energy is usually a lot less than the chemical energy. So consider the burning of isopropyl alcohol, making carbon dioxide and water. What we're saying is the reactants have more chemical energy than do the products. So energy is transferred from the chemical system to the thermal system, or account, I should say, excuse me. So the temperature increases, the system is now hotter than the surroundings, and as a result, energy will flow via heating from the system to the surroundings until the system returns to its thermal equilibrium with the surroundings. And if you want to see more detail, I have put a PowerPoint in the folder, which is going to be shared with you, that gives lots of examples, both of exothermic and endothermic reactions. Biology is a bitch. Sorry about the language there. It's just harder because it's difficult to distinguish system and surroundings. I'm going to pause for just a bit, give you a chance to get a breather. I have 4:30 or 7:35 now, and I'm going to give you the opportunity to ask questions.
So Larry, there's a question in the chat. Can you say it is just like extending a spring a bit more, putting a little more work in so that the spring bounces up and down more than it did before? That came from Barbara. So Barbara, if you want to unmute and explain your question, because she posted it a while ago.
Got it.
It was just in response to Melissa's question about a simple way of explaining why things should vibrate more if you increase the temperature.
When those particles, you remember Molly and Marvin, the two little popcorn pieces that were connected by a spring? Well, if they get bombarded by surrounding particles, that's going to increase their motional energy. And so then they would end up vibrating back and forth. So it's not just the motion of the particles, because they're not free to move about. They are bound in the condensed phase. So I'm increasing both the kinetic energy, that is the actual motion, but also the energy stored in the field that is connecting these, interacting with these particles. I hope that helps.
New question in the chat, Larry.
Okay, hold on. I'm scrolling to see parts of the system going.
No. Could you give an example where the transfer is through radiation? For example, if the sun heats something and changes its temperature, should you use Q or R?
Oh, I think that primarily I would use Q. If I'm talking about chemiluminescence, then I have where I have like a glow stick or something like that, then I would use R. Their photons of light are emitted from excited these molecules in these oh geez, I can't think of the term I'm trying to use. These molecules in excited states. In the chemical reaction, electrons are pushed up to excited levels, and then they take a while, and then they come back down and they emit light. So I would use R for that particular thing. And you don't have to say energy flow. I just try. That's a generic diagram, and you could take flow out if that's what you wanted. All right. Okay, thank you for the folder. Could you give an example where it transfers through radiation? Oh, when we talk about photosynthesis in biology, chromophores in the plants are absorbing energy, photons of energy from the sun, and that creates excited states, and that drives chemical reactions. When do I ever use energy radiation in an energy bar chart? Oh, chemiluminescence is one that I'm thinking of. Ready to move on?
How do you deal with representing gravitational energy in the bar chart if an object is in the system and the Earth is out of the system?
Oh, this is an excellent question. You know, when I first got exposed to this thing with energy bar charts, Alan Van Huvelen, who was at Ohio State University and then he went to Rutgers. He may be retired now, I don't know, but he did a presentation on this on our local AAPT meeting, and he gave us several examples like Earth in the system, Earth out of the system, and you could smell the gear oil burning in a room of physics teachers as we were trying to figure this out. If the Earth is out of the system, then it's an external agent, and it's applying energy to the system via working. So the Earth is applying a force to the object, which is causing it to either slow down if it were moving upward or speed up if it were moving downward.
Do you make the field an object in the system schema?
Remember, we are describing energy with a substance metaphor. You know, energy isn't substantial, okay? It's energy flows, matter changes. So the energy isn't a stuff. You address energy loss due to friction. You know, internal, you don't love the internal term that I've seen. Yes, I understand. When objects experience frictional forces, that usually changes the motion or configuration of the constituent particles. So you can't have friction with point particles. You have to have extended bodies. So that's where it gets to be more complicated. And in fact, if you look at the physics notes on energy in the modeling physics materials, they talk about elastic kinetic gravitational energy of the point particles. And then if you go down, if the particle has internal structure, because it's an extended body, then it has internal particles that have to undergo these kinds of motion or whatever. Jeff suggests that friction transfers energy to the thermal account. Yes, that is true, but we don't generally use mechanical energy. Oh gosh, we love these terms. What do you mean by mechanical energy? Are you talking about recoverable kinetic energy? So working by friction. So you want to have, Jeff, you want to have an object. See, I think you only have friction when both the object and the surface are in the system. I don't want to have the desktop applying a force. Then where does if the temperature increases, then what's going on? Am I increasing the temperature of the surface, the object, or both?
Sure. If the surface is not in the system, then energy is leaving by working.
Or by heating. It could be leaving by heating.
Some of both, right? Depends how down in the weeds you want to get with your students.
It does, and I will be happy to send you a wonderful set of articles on friction and energy.
But the term mechanical energy, I think, is an old-fashioned term and to be avoided. It's in my bad word jar with potential.
Absolutely. Just like physical change is in my bad word jar as well. Okay, I want to make sure that I get to the biology part. How many biology teachers do we have in the room? Raise your hand. Oh no, were they all afraid to attend?
Well, after what you said about biology, maybe.
I didn't say anything. I just said biology was a bitch. I mean, I have I have immense respect for people who teach biology because it's so darn hard. Okay.
I see one hand raised. We have at least one.
I did. Amanda has her hand up. Okay, Amanda, this is for you. Okay, so let's see. I need to get back to my PowerPoint. And I am going to. Okay, so why is biology difficult? Well, it's hard to distinguish system and surroundings, and the reactions are often coupled. For example, I have the oxidation of glucose to make carbon dioxide and water, providing the energy that is required to synthesize ATP from ADP. These two reactions happen side by side. And how can the energy bar charts get more complicated? So I'm going to let you look at that for a while. We have two parallel energy bar charts. The first one has the oxidation of glucose, the products store, oops, darn it, didn't mean to do that. I got to move this guy out of the way. There we go. The products store less chemical energy than the reactants do. Ordinarily, if I were just burning the glucose in a petri dish or something like that, the thermal energy would go up and then energy would leave the system via heating. But since we don't have plain old flames going on when we are oxidizing glucose, we have enzymatic processes where the energy is transferred to this coupled reaction. And in this particular case, you can see that the chemical energy stored in the ATP is greater than that stored in the ADP. Now, you're going to say, wait a minute, you don't do anything with thermal energy. And the answer is, you're right. I admit it. We're models are simplified representations of physical systems and processes. We'll get to the more complicated one version in just a bit. All right, so maybe as a biology teacher, you might say, I'm not sure I want to go do this energy bar chart with these coupled reactions. But at the very least, what you could do is you could avoid promulgating the high energy phosphate bond misconception. This is something I picked off the internet, and you know, if you see it in the internet, it's got to be true. Okay, but we want to talk about this particular bond. When you break the terminal phosphate from ATP, that bond breaking doesn't release energy. Bond breaking always requires energy. Bond formation releases energy. And part of the problem is the simplified version, we're trying to do students a favor and we end up hurting them, it neglects the role of water. So when this terminal phosphate combines with water to make the hydrogen phosphate ion, what you've got to use is the lottery ticket metaphor. I spend a small amount of energy to cleave the terminal phosphate from ATP. That's like buying your ticket. And then I get a larger amount of energy back when the phosphate combines with the water to make the hydrogen phosphate ion. Bond breaking requires energy. Bond making releases energy. And so if you just keep mentioning as a biology teacher that it's the hydrolysis of ATP that provides the energy required to drive biological processes, rather than just saying ATP just magically becomes ATP, then that really helps. Sorry about this. I'm bopping back and forth. I don't mean to be. So if I look at the second part of this system here, where I'm using ATP to drive processes, ATP stores more chemical energy than the ADP. When under the hydrolysis reaction, gosh darn it, the energy flows into doing any one of those processes I showed on the previous slide. Moving flagella, driving ions across gradients, synthesizing proteins. All of those processes require energy, and this is what happens. So the thing that all of these are endergonic, and the synthesis of ATP provides the energy to do that. Okay. Now you've been sitting there saying you've been very good. You've been saying, okay, you haven't been doing anything with thermal energy. You're right. So at the risk of insulting you, I'm going to read you this little paragraph here. In all of the chemical reactions and biological processes described above, some energy ends up in the thermal account. I just haven't been showing it. For example, only about 20 to 25% of the energy from the hydrolysis of ATP is captured in the kinetic energy of muscle contraction. Some of this thermal energy is radiated to the environment. For mammals and birds, some of the thermal energy is used to maintain relatively high body temperature. That's thermal regulation. You're likely to read that thermal energy or heat is produced in various sources. We don't want to use that language because we don't want to imply that energy can be created. Come on. A more realistic, but unfortunately more complicated energy bar chart is found on the next slide. Okay, ready? So here we talk about the inefficiency of biological processes. I'm going to hopefully make this sense. Here is glucose going to carbon dioxide and water. 3 bars of chemical energy are available from the combustion of glucose, but let's say that 1 bar is lost to the surroundings just by heating. That means only 2 is available to drive the synthesis of ATP, but even that process wastes some energy. And so I'm losing 1 2/3 bar out of my original 3 bars. That only leaves 1 1/3 bar left. So I'm going from 3/3 up to 7/3. So some of that energy is lost when I'm making ATP. In the next processes where I'm doing the hydrolysis of ATP, some more energy is lost in that enzymatic reaction. So now only a smaller chunk of that energy is available, to drive the structural changes that I was talking about, because some of the energy is, again, lost via heating. So only about 1/9, or roughly 10%, of the energy that was originally available in the glucose that I was burning is actually doing useful work. And that's sort of consistent with the energy account that we talk about when going from trophic level to trophic level. Now, if I were a biology teacher, would I show this as my first step? Not unless I wanted everybody to drop the course. I mean, what you do is you say, if you're inquiring minds, we'll go into this, but let's simplify. Remember, models are simplified representations of processes. Well, if you go to this link, and Erica, can I put this link in the chat window?
Yes, please just copy and paste it in. I can't because I don't have the PowerPoint, but yeah.
Yeah, but I can try to get that, and let me see if I can go to that.
And while Larry's doing that, and we'll go back to Larry in a second, I wanted to let everyone know, if you need a certificate of attendance, I am going to put my email address in the chat now. You will email me with your first and last name, how you want it to appear on the certificate, and you will get 1 PD hour. And I'll email you the certificate probably by the end of the week.
Okay, so an annotated version of this presentation is at that video link. I think, Erica, you were going to share the link to the folder in which all these resources was.
It's actually going to come from Carly in the chat, but yes, it's going to come in the chat right now, and then we will post it on the member portal for people who could not attend who are members.
So you'll get the presentation. You'll get, actually, the presentation is available as Google Slides as well as PowerPoint, those of you that don't have Microsoft. You'll have the video clips, and then also another PowerPoint presentation that talks about chemical energy. There's also, excuse me, I'm going to show you this for those of you who have to try and talk with your colleagues about this. Let's see if I can find, oh, come on, I want to be able to get to, there is a Google Doc called Energy and Modeling Instruction, both a Word and a Google Doc. It's a 2-pager. So it's a nice little summary of what I was talking about, where I talk about our 4 big ideas, our transfer mechanisms, how energy is stored, either in motion or in configuration, and then a collection of the different accounts and the definitions. So you're welcome to use that. If you think that might be something you might hand out to students or colleagues or whatever. Okay, I got 5 minutes to go. What do you want throw at me here? There are links to the materials and the articles on friction and energy. Yeah, it'll take me a while to dig those up. I wasn't counting on that question on friction. Thanks, Jeff. Good job. All right. I'll see what I can find for you there.
I have a question about your biology bar charts.
Okay.
So you had two bars. I wasn't paying close enough attention before you showed the complicated ones, but in the complicated ones, there was 2 bars of thermal energy in every bar. And
Yeah.
I've been trying to encourage my students to, if the energy in an account doesn't change, you don't need to be focused on it. You don't need to include it. Is that a
You're
mistake?
absolutely, that's an absolutely appropriate strategy. Am I sharing my screen or not?
Not at the moment.
Not at the moment. Hang on a second here. I'm going to go back to Zoom and share the screen. Boom, boom. Now do you see it?
Yes.
Okay. So Jeff says, do we need to have thermal energy if it's not changing? And the answer is no, you do not. Okay. I just put it there because people ragged at me when I didn't have it in there in the first place. What else? Erica says she thinks bar charts are appropriate for middle school. Absolutely. They're qualitative, you know? And in fact, the cool part about it is that it helps you figure out what equations to use if you're going to be doing anything quantitative. Do we have a source or two for presenting this in a more simplified version to middle school students?
I would ask that person if they have, let's see who posted that. So Allison, in the chemistry materials, there is a PowerPoint presentation that I believe was put together by Larry that is designed for teachers, that explains how to use bar charts. I'm curious if you have access to that.
It's in the folder that Carly just put a link to. Now it's PowerPoint, because I could convert it to Google Slides for you. You should be able to.
So there actually is a little bit of stuff about energy bar charts in the middle school curriculum in AMTA. I can't remember exactly where it's at, but it's in there.
I believe you are right.
Carly might know. Carly does middle school.
Yeah, so can you guys hear me?
We can.
Okay. So yeah, the middle school curriculum has energy bar charts throughout a lot of it. So in every, grade level, it kind of touches on it a little bit more too. And it's tough for them, but after a while they start to grasp the concept. So
Rachel mentioned a different representational tool, pie charts. Pie charts are fine as long as you have a closed system. All right. Because then you can have the pie divvied up different ways depending on which account the energy is being stored in. I just find it less helpful when I have energy entering and leaving the system. Well, you've been a great audience. I was afraid that I'd end up with 10 by the end of the hour, It looks like a bunch of you are still here. I haven't scared you off. So I hope this helps. You have
Larry, Jim has a question. Can we answer it real quick before we go?
I can try. Do I
Could
see
you
it?
please explain why physical change is such a bad word?
Oh, the reason for that is the definitions I used to see. In fact, the chemistry books are finally getting rid of that. They used to say physical changes are reversible and chemical changes are not reversible, but that's not true. Can I easily reverse that change? No. And I'll have a whole chapter in my chemistry book called Chemical Equilibrium, which talks about reversible change. So I think phase change and chemical change are more useful terms. I remember I was at an ACS meeting where we had somebody, I swear, was ready to hold a crucifix up next to me because I was talking about dissolving as a chemical reaction. And the person said, no, it's not. And I said, yes, it is. Because when the water molecules are solvating the ions in solution, that's a structural change. Now, it is true that some of the water molecules are just going faster or slower, but some of the water molecules are actually involved in structural change. So I'm just thinking, I think if we just eliminate physical change, no one's going to miss it. We talk about phase change. That's cool. There you have the particles being separated from one another, from solid to liquid, and moving around really fast when they go to gas. But hey, I'm keeping you longer than I should. So should we just wrap this up? I mean, it's only 5 o'clock my time, but I think for some of you guys on the East Coast, it's getting kind of late.
Thank you, everyone, for showing up. Please email me if you have any questions.
Was my email address in the webinar description?
I don't believe so. We can post it when Carly posts the folder in the and the video. We can include it then.
Yeah, so I won't mind if you send me emails.
Well, if they send me any, I'm gonna just pass them on to you.
Okay, you can also BRBO me money too if you want, but not BRBO. What's that called? Venmo. You can Venmo me money if you have my email address. But
so Frank, these will be posted on the AMTA member portal, so you will log in, and under resources there'll be a tab where you can click on recent webinars, and it'll be recorded there.
And as I said, the Vimeo link, did I send it to everybody?
Yes, in the very beginning, it was on the very first slide.
Okay. Well, I believe
so it's in the folder. Like if they go to the slides in the folder, they will have it.
Yep, it is. Jim, your hand's still up?
Larry, I just have a question.
What we got here?
That's Nell.
Yes, I just have a question for you real quick.
Oh,
I do teach middle school, and when you were referencing the hand with the ball and the gravitational energy, and you had mentioned that the energy was stored in the gravitational field, I know this might be a silly question, but where exactly is that field? Does the field exist between where that object is and like the center of the earth, or where exactly is the field?
Yes, you described it perfectly.
Okay.
So,
okay, thank you.
So you had, I suppose, there's one metaphor that's often used where people take a stretched sheet and they put a heavy mass in the middle of it, and it shows how the Earth warps space-time. That sort of gives you some impression. So an object will placed close enough will be is attracted. So that's one representation. You could see, you could talk about a rubber band connecting the Earth to the object that's off the Earth.
Okay, I just wanted to make sure that I was clear on my understanding of where that field exists.
Everywhere around the particles that have mass.
Okay, thank you.
You bet. We still have a few hangers on here. Do they have questions or?
Thanks, Larry. It was good to see you.
You bet, Beth.
Take care.
It's been a while.
Bye, Larry.
See you, Laura. How you doing?
I'm all doing okay.
Glad to hear it.
Bye, thanks very much.